This lesson is an extension of the concept of work done by a variable force. And if you remember from the last lecture, we looked at springs that had a linear force, and since the force changed depending upon how much the spring was stretched or compressed, we used this expression for work because it was fairly simple to come up with an expression for the force as a function of position or as a function of how much the spring was stretched. In this situation, when we're talking about things like pumping water or lifting a hoist, it becomes more convenient to define work in terms of incremental work done. In other words, in these situations, we're actually lifting something, but we're lifting it a varying distance. So we might be taking a part of an object and lifting it 1 meter, and then we're taking another part of the object and lifting it 4 meters. So in that situation, when we actually have almost a constant force but a varying distance, it becomes more convenient to define work in terms of incremental work done. And so the first example that we're going to go through is going to involve pumping water out of a tank. And so if we look at this example, we have a tank here, and we're pumping water out of this tank. So if this tank is full, we start by lifting the water at the top just a little bit to get it out the flow tube, the horizontal tube. But if this tank is nearly empty, then we're lifting this water out of much greater distance to get it to that horizontal flow tube. And so if we look at this, the way we can approach this then is we take a look at the incremental work done. So we have to, the easiest way to do this is to come up with an incremental work delta W. And that delta W is going to be based on the weight of the object being moved. And in this case, we're going to take a small sliver of water. You can see it in the darker blue here. That's really that small disc of water is a circular prism or a cylinder. And so that's going to be the weight of water moved, and then we're going to multiply it by the distance we have to move it. Because we know weight is a force, and distance, if we take that force times distance, that is the definition of work. So the weight of the water then is going to be its mass times the gravitational constant. And then times distance. And so then we get then we get into, well, how do we define the mass of water here? In order to define the mass of water, we need the density. So here's our density. And we notice that this is density because it's actually a weight density. Okay, which is why this notation is a little misleading. It doesn't weigh that much, but it is a weight density because we notice it is force per cubic meter, and that's the definition of density is a unit of either mass or weight per volume. And so we're going to then calculate this mass by taking the density per unit volume and then times the gravity. And so the gravity then is this weight density then is really, this weight density then is this mass density times gravity. So we can rewrite this as the weight density times the volume times the distance that we have to move. And so that distance that we have to move then is becomes that function, so to speak, because it does vary depending upon where the disk is located, whether it's at the top or at the bottom. So the weight density is a constant. For water, it's 9,800 newtons per cubic meter. You might notice that is 1,000 kilograms per cubic meter, or a gram per centimeter cubed, if you remember from chemistry. And the volume then becomes the volume then becomes the incremental portion of this expression. So what I'm going to do is I'm going to kind of squeeze a delta in here. So it's really the incremental volume that we're lifting, and we're going to lift the same incremental volume. We're just going to lift it different distances. So in other words, if we're lifting this thin cylindrical disk of water, then the area, of course, the volume here, the delta volume, is going to be the area of the base times its height, and that height then becomes our incremental expression. So this height is actually our dy. And of course the area of the base here, we're talking something that's circular. So we're talking about pi r squared delta y, or dy. And so, and of course the radius is just from the center out to the edge, and that is a constant as well. So for this expression then, the expression of the incremental work done, we're looking at a density of 9,800 times the incremental volume, which is going to be pi radius squared delta y, and we'll change that to a dy when we put it into the integral, and then the distance. And so like I said, in order to determine the distance moved, the distance is going to vary depending upon where this disk is. In order to determine that, we need a coordinate system. And the easiest thing to do is to place your coordinate system down at the lowest elevation. So if we place our coordinate system down here, then if this is our origin right here, then if this is the level of the disk, this distance ends up being y. But what we're doing really is we're taking this disk and lifting it up to here. And if we look at the details of this problem, we have a 4-meter high tank. So the whole tank is 4 meters high. And the tank is buried 1 meter below the surface. So this is 1 meter. So if we're lifting up this height here, which is y, then the distance we have to lift the disk is this distance here. Okay, so that distance then, let me just highlight that in a different color. That distance is the amount of distance we have to lift the water, and that distance then, there we go. That distance then is, let's see, that the pipe is up here at 5 meters above the bottom, above the origin, and so if this is y, then this distance here is 5 minus y. And so the distance that it's moved then is 5 minus y. So here is the incremental work that's done. So now what we do is to calculate the total work, of course, we need to integrate the incremental work. So we need to integrate this expression. So we're looking at 9,800 times pi times the radius, which is 2. 2 squared. This is your dy times 5 minus y. So rearranging that, of course, let's see if I can just move this stuff. No, I can't. Okay, so rearranging that expression then looks like, let's see, 9,800 times 4 is 39,200 pi times the integral of 5 minus y dy. Now we have to look at the limits of integration, and the limits of integration are always relative to the coordinate system that you set up. So if we fill this tank completely, let's assume that it's completely filled to begin with, then we are removing water from an elevation of 0 to an elevation of 4. So those become your limits of integration. And so if we do a quick check here, this is the elevation, so this stands for the y. If we stick the 4 in here, that represents the top of the tank. 5 minus 4 is 1. We're lifting the top of the tank 1 meter out to the flow pipe. And the 0, we put 0 in here. 5 minus 0 is 5. 0 represents the bottom of the tank. So at the bottom of the tank, that water is being lifted 5 meters. So that's kind of a way you can check to make sure your limits of integration are correct. If you notice, the integration becomes pretty simple at this point. So, and that's pretty typical of problems like this, when you have the variable function being the distance being lifted. You do end up with pretty simple integrals. So I'm going to go ahead and integrate this by hand. We have 5y minus y squared over 2, and that's from 0 to 4. And so substituting in the limits of integration there, you're going to have 39,200 pi, and putting 4 in here is going to get us 20. Putting 4 in here is going to get us 8, I believe. 16 divided by 2 is 8. And so 39,200 pi times 12 should be the amount of work done to empty that tank. So if we come back here and just do a quick calculation here, let's just make sure that 9,800 times 4 was right. Yep, 39,200, and then times 20 minus 8, that is 12, equals, okay, so that ends up being 470,400 pi. And let's see, we're measuring in newtons and meters, so that's a Newton meter. That also is also known as a joule for those of you who are taking physics right now. So there's the amount of work required, and you can multiply the pi through there if you want to empty that tank, pump it out to the top. Just an aside, from a practical application standpoint, if any of you are familiar with pumps, this is not realistic, okay? We don't really suck water off the top of anything. We usually just stick a tube all the way down to the bottom and lift the same amount of water off the bottom, which becomes a much easier problem to determine how much work is done. It ends up being more work, but it's a lot simpler to calculate, and then we just oversize the pump to handle that additional work. In this example, what we're doing is we're using a winch or a motor with a drum on it to wrap up cable and raise this cable up from down here to up there. So again, this winch is doing some work, and the amount of work that's being done, again, it's the most convenient way is to look at that concept of incremental work. Because we're lifting different parts of the chain different amounts. And this one's also a little more advanced because it's not just a variable work, there's also a constant work component to it. So let's try to split this apart here into what's changing and what's not changing. So if you notice, we're talking about winding up 1/3 of the chain, and the chain is 15 feet. So if this is 15 feet, you know, as we wind up the chain here, if we're winding up 15 feet of chain, that's a bad line. Let me do this. There we go. That looks better. Okay, if we are winding up of 15 feet of chain, okay, and we're only winding up 1/3 of it, that means we're winding up 5 feet. So then what is left? We have 10 feet of chain left. That makes sense. So what we're really looking at, like I said, is a combination of constant and variable work. This 10 feet of chain, is literally this bottom section just lifted vertically. And so we have this, in fact, let me just kind of get rid of that. We have this, and we'll talk about the constant portion first. The total work then is going to be this constant portion plus this incremental portion. Okay, so this constant portion comes about from the bottom 10 feet of cable, because that bottom 10 feet is just literally being lifted straight up into the air. So if we could just take this, and group it, and actually let's change its colors to green, just to kind of, and then what we're going to do then is we're going to copy and paste. So this bottom 10 feet right here, which is represented right there, that bottom 10 feet is just being lifted straight up. It's not being modified at all. It's not being shortened at all or anything. So that's your constant part. So if we take a look at the that constant part, then, in fact, I'll try to color code this a little better. That constant part is 10 feet of cable, and so we have to figure out the weight of that. So we have to figure out the weight of 10 feet of cable, and then times how much we lifted it. And so we lifted that 10 feet of cable 5 feet. And so if we take a look at the problem here, the chain weighs 3 pounds per foot. So 3 pounds, 10 feet, we've got 30 pounds. And we lifted that 30 pounds 5 feet. So the constant portion is 150 foot-pounds. Okay, so that's the constant portion. Now there's a variable portion to this problem as well, and that's what we are going to need for integration. And this variable portion is this portion of the chain that is being wound around the drum. That's the part that's being coiled around the drum as the drum rotates. And so if we think about, you know, this is a chain and it's got links and stuff like this, this top link up here is only lifted a very little bit. And this bottom link is lifted 5 feet. So again, just like pumping the water out of the last example, we have that variable component of this, even though the links are identical and each link weighs the same amount, they're being lifted different distances. So we're going to take an incremental link somewhere in the middle, so to speak. That's going to be our dy, and we'll consider that that incremental link at a distance of y above the origin. So again, when it comes to determining your coordinate system for these type of problems, I always pick my coordinate system to be the lowest portion of that variable part of the picture. So there is my origin, and so this incremental link is a distance of y above the origin. And so the lift, which is this, this portion that we're lifting, this incremental link from this location up to the drum. So this is our lift function, or our distance function. And we're talking about lifting it 5 feet. So our distance function is 5 minus y. And so if we look at the variable portion of work, and I'll write down here, the variable portion of the work is the incremental weight times the distance function. So again, that incremental weight is that we have 3 pounds per foot. That's our linear density. And then we need a linear length, and our length is our incremental function dy. So there's our weight. We're lifting 3 pounds per foot for each foot of cable lifted, and then our distance is 5 minus y. So there's our incremental portion. I guess I could call that delta y technically. And so to figure out our incremental weight, then to figure out that total, we're going to have to integrate. And so we're going to have to integrate 3 times 5 minus y dy. And again, to get the limits of integration, we're going to have to come back to the picture and say, well, where is the chain that we're lifting? The chain that we're lifting is starting at the origin and going all the way up to 5 feet. So we'll have a lower limit of 0 and an upper limit of 5. And again, like I mentioned before, these get pretty easy to integrate. And so really we're just integrating a 5 minus y dy. And so that is 5y minus y squared over 2 from 0 to 5. And plugging in the limits of integration, then 5 times 5 is 25. And y squared over 2 is 25 over 2. So we're looking at, and then plugging in 0 is just 0, so I'll just drop that off. So we're looking at 3 times 12.5. And so 3 times 12.5 is 37.5 foot-pounds. So the total work then is going to be our work that we get from our constant work function plus our variable work function. So we're talking 150 plus 37.5, which gets us to 187.5 foot-pounds. Here's a similar lift problem, and to the last one, we're coiling up a cable around a drum using a lift or a hoist, and in this case, we're going to coil up all of the cable, and in addition to that, we're going to have a load here of 500 pounds. So like the last problem, this then, since we have a chain that is getting shorter and shorter, we have a a constant work component, and that's just the load being lifted, and we have an incremental work component, which is the chain being wound up. And so if we talk about our constant component here, that's going to be the weight of the ball times the distance the ball moves. So taking a look at that, we know the ball weighs 500 pounds, and the distance that it is moving is 40 feet. So we're going to wind up all 40 feet of cable. So the constant portion then is 20,000 foot-pounds. Okay, now we've got to take a look at the variable portion, and that variable portion it has to do with the cable being wound up. So here's our cable. Again, we're going to start our origin at the lowest portion of that variable component, and so we'll take an incremental portion of wire here, dy, and we're going to measure then that according to our coordinate plane. That's going to be at an elevation of y above the origin, which means our lift then, the amount that incremental section of cable is being lifted, is going to be the 40 minus y. So that's the amount that's going to be lifted. So the incremental work here then is going to be our incremental weight times our incremental distance here, or incremental length. So we're going to have our linear weight again, and so our weight per foot times our linear distance, our incremental length, delta y there. So our weight per foot, this cable weighs 1 pound per foot. So let's not lose sight of that fact that ones kind of tend to disappear, because when we multiply by 1, we don't change the value. But we have 1 pound per foot times an incremental distance of dy, or delta y. And so that's our incremental work. And so as we integrate that, we're going to integrate then, that's our weight, now our distance. So our distance that we're lifting that incremental section of cable is 40 minus y. Almost forgot the most important part there. So we are integrating then 40 minus y dy. And again, this cable is present throughout this entire variable portion. So we're going to be lifting that cable down at the 0 mark and also up at the 40 mark. And as we integrate that, we're going to get 40y minus y squared over 2. Evaluated from 0 to 40. And when you evaluate that from 0 to 40, you get, let's see, putting in 40 here is 1600, and putting 40 here is 1600 divided by 2, that's 800, I believe. And so the work associated with winding up the cable is 800 foot-pounds. So the total work then is going to be the 20,000 foot-pounds from raising the load, and the 800 foot-pounds from coiling up the chain. So we're looking at 20,800 foot-pounds for the total work to lift this 500-pound load. Here's an example of Boyle's law, And Boyle's law really is just the relationship between volume and pressure, if you remember from chemistry. And so you don't really have to remember chemistry. That's not really what they expect you to remember when you're taking an AP Calc exam. They're going to actually come right out and tell you that the pressure is inversely proportional to the volume. Okay, so that's the definition of Boyle's law. And so, like I said, you don't have to remember the chemistry. Just be a critical reader, and then you can set up an inverse proportionality, right? As one goes up, the other goes down. And we'll give it the proportionality constant K. And so the first thing we have to do is figure out what that proportionality constant is, and we'll do that with the rest of the information here. And then we're going to have to go ahead, and as the volume varies, we're going to have to integrate that to find the pressure. So it says that the quantity of gas with an initial volume of 1 cubic foot and a pressure of 2,500 pounds per square foot expands to a volume of 3 cubic feet. And so we want to know then what is the work associated as that expansion takes place. And so we're going to use this information here to find our proportionality constant. So we have 1 cubic foot, and we have a pressure of 2,500 pounds per cubic foot. And so we're going to go ahead and find that proportionality constant. So little cross multiply here, our proportionality constant is 2,500 pounds. And so we know then that this relationship is this, 2,500 over the volume. Okay, and now we're going to go ahead and allow that expansion to occur. And so in this situation, and for reasons that you would get into if you're taking a course like AP Physics B, but work is, we know work is force times displacement. Work is also pressure times change in volume. So that being the case, and I know I'm kind of glossing over the reason why, but I'll let your physics teacher take care of that. So the total work then, we can get just by integrating both sides. The total work then is going to be your pressure function with your differential being the dV, which is why we're talking about expanding the volume to 3 cubic feet. That kind of gives you the idea that the volume is the differential expression. So the total work here then is our pressure function, 2,500 over the volume, dV, and the variable of integration is volume, and we're starting at 1 cubic foot and we're expanding to 3. And so if volume is the differential expression, then this is just a 1 over V integration. So we're really looking at 1 over V dV, and that ends up being the natural log of the absolute value of V from 1 to 3. And so we are looking at 2,500 times the natural log of 3 minus the natural log of 1. And putting that into your calculator gets you a work of 2746.53 foot-pounds.